Metabolism encompasses all the processes and pathways needed for cell survival. These processes can be classified as catabolic processes or anabolic processes. Catabolic processes involve the breakdown of dietary components with the purpose of producing energy, most likely NADH and FADH2, which are eventually converted to ATP, a more readily usable form of energy. Anabolic processes will use the ATP produced from catabolism to synthesize cellular components like proteins, carbohydrates, lipids, membranes, nucleotides, nucleic acids, and other macromolecules, as well as maintain other cellular processes. Metabolism is compartmentalized. Some of the most important anabolic pathways occur in the cytoplasm. This includes glycogen, fatty acid, triacylglycerol, cholesterol, and nucleotide biosynthesis, as well as amino acid biosynthesis. On the other hand, some of the most important catabolic processes occur in the mitochondria, including pyruvate dehydrogenase, TCA cycle, fatty acid beta oxidation, and glutamate dehydrogenase, with glycolysis, glycogenolysis, and HMP pathway occurring in the cytoplasm. It is noteworthy that the urea cycle and gluconeogenesis start in the mitochondria and continue in the cytoplasm. There are three stages of catabolism. Stage 1, which occurs primarily in the intestinal lumen, involves the digestion of dietary components, polysaccharides, proteins, and triacylglycerols into their building block components, glucose, amino acids, fatty acids, and monoacylglycerol, respectively. Glucose and amino acids are picked up by the enterocytes and eventually released into the bloodstream, whereas digested lipids, fatty acids, and monoacylglycerols are reassembled into a chylomicron triacylglycerol-rich molecule and then released into the bloodstream. After their pickup from circulation, glucose, amino acids, and fatty acids are catabolized inside the cell, either in the cytoplasm or the mitochondria, to produce high-energy molecules. Of the four major catabolic pathways, only glycolysis occurs in the cytoplasm, whereas pyruvate dehydrogenase, the TCA cycle, and fatty acid beta oxidation occur inside the mitochondria. The NADH and FADH2 produced by the three mitochondrial catabolic pathways will be present in the mitochondrial matrix and will be directly accessible for the third stage of catabolism, which occurs inside the inner mitochondrial membrane. The purpose of the third stage of catabolism is to convert the high-energy molecules NADH and FADH2 into a usable form of energy that can be readily used by the cell, namely ATP. This occurs through the coupled process of electron transport and oxidative phosphorylation. Glucose has at least 4 uses in the cell. The first one is through glycolysis to produce energy and 2 molecules of pyruvate. The second one is in storage of glucose as glycogen, which occurs in both liver and muscle. The third one is in the hexose monophosphate pathway or pentose phosphate pathway, which produces NADPH and pentose phosphate or ribose phosphate needed for nucleotide biosynthesis. The fourth important use is in glycosaminoglycans, which are important extracellular matrix components, and the glycolipids, which are plasma membrane components. Fatty acids play at least 4 important roles in energy production, in energy storage, in membrane synthesis, and in inflammation. Fatty acid beta oxidation in the mitochondria is the major energy producing pathway from dietary and stored lipids. Fatty acids are stored in the form of triacylglycerol in adipocytes and provide many tissues with the energy they need during fasting. Phospholipids, the major membrane components, are made from fatty acids and glycerophosphate. The essential fatty acid, linoleic acid, is the precursor of arachidonic acid, which in turn is the precursor of all eicosanoids. There are 4 distinct uses of amino acids from dietary proteins. First one is to provide amino acids to rebuild tissue proteins that have turned over earlier. The second important purpose is to provide the carbon skeletons from amino acids to make glucose in the liver to restore blood glucose. The third important use of amino acids is in the synthesis of purines and pyrimidines needed for nucleotide synthesis. The fourth important use of amino acids is in specialized products like heme, catecholamines, and porphyrins. Glucose, a 6-carbon monosaccharide, is catabolized sequentially by glycolysis, pyruvate dehydrogenase, and the TCA cycle to yield 8 ATPs, 6 ATPs, and 24 ATPs respectively, for a total output of 38 ATPs. Dividing 38 ATPs by 6 carbons in glucose will give you 6.33 ATPs produced per CO2 produced. Beta oxidation of fatty acids is the major catabolic pathway that produces energy from dietary triacylglycerol or stored triacylglycerol. Starting with palmitate, a 16-carbon fatty acid, beta oxidation will sequentially remove 2 carbons at a time in 7 cycles to produce a total of 8 acetyl-CoAs at the end. The total net ATP output from the complete oxidation of palmitate to CO2 is 129 ATPs produced. which is equivalent to 8.06 ATPs produced per CO2 produced. If you like this video, please subscribe. Thank you.